Okay, so now we're moving on to the topic of divergence, which is going to be defined in a way that's going to look somewhat similar to the definition of curl, but it is different. Um, so before we get into it, I want to just point something out. We've used the term divergence in calculus before. You use it a lot in calculus too, where you talk about sequences and series either converging or diverging. This is a completely different use of this term. So there's no connection between what we're calling divergence, in this case, divergence of a vector field, and the divergence of a series or a sequence. A little bit later, we'll go ahead and talk about this now. In the previous video, I talked about how curl represents a tendency of a fluid represented by the vector field you're taking the curl of to rotate about the axis aligned with the vector that you get from the curl at a particular point. So we think about it in the terms of fluid dynamics and the tendency of a fluid to rotate about an axis. Divergence is also a concept that relates to the idea of a vector field representing a fluid. If you calculate the divergence of a vector field at a given point, that quantity represents the tendency of the fluid to flow into that point or away from that point. And when the divergence is positive, the fluid has a tendency to flow away from a point. When something is, we think of that as the fluid diverging away from that point, which is why we call it that. So let's talk about the definition of divergence for a second. Again, we're talking about a vector field F, which is equal to Pi plus Qj plus Rk. P, Q, and R are the component functions. The divergence is defined to be the sum of these partial derivatives. Partial derivative of P with respect to X, Q with respect to Y, R with respect to Z. If you notice, that is the dot product of our del operator with F. And if you want to see that, here's our del operator, partial with respect to X, partial with respect to Y, partial with respect to Z, and if we dot that with the vector P, Q, R, notice you're going to get the partial derivative of P with respect to X, Q with respect to Y, R with respect to Z, and the dot product will sum those things. That's exactly what we have here. Okay, so I talked about a little bit about the meaning behind divergence in terms of fluids. Again, positive divergence at a particular point in a vector field is the tendency of a fluid to flow away from the point. In that case, we call that a source. The point is called a source. The idea is that if you imagine a pipe that's feeding into this vector field at that point, if it's pumping the fluid into this vector field, then the fluid will flow away from the opening of that pipe. So we call that a source. If the divergence is negative, we call at a particular point, then we refer to that point as a sink. Sink meaning if you can imagine in a fluid placing a drain at that point, the fluid will flow toward that drain and sink into it. If the divergence at a point is equal to 0, then we say that the fluid or the vector field that represents that fluid is incompressible at that point. Okay, and this is fluid dynamics. Again, this is not a course in fluid dynamics, but it's really the most natural interpretation of a lot of what we do here. So we'll keep talking about things in those terms. Let's practice finding the divergence of a vector field. It's easier than finding the curl because it's not a full determinant that you need to find. Here, if I want to find the divergence of F, that's del dot F, okay, where this is my function F. So what I need is the partial derivative of this first function P, which we're calling this P, with respect to X. Notice there is no X in this function, so the whole thing is treated like a constant. It's 0, I. The next one, we're going to take the partial derivative with respect to y. But again, x over z, there is no y in that term. So this goes to 0 as well. I get 0j. Finally, I want to take the derivative of my last function with, sorry, I shouldn't be including these i's and j's here. Let me back that off for a second. Notice we should not be getting a vector field as the result here. It should be a scalar field. So I want to be careful to not put those i's and j's there. Finally, we take the derivative of this with respect to z. There is a z present here, and y cubed is what's left. So minus y cubed at the end of that. The divergence then is negative y cubed. Okay, so again, the divergence of a vector field is a scalar field. The curl of a vector field is a vector field. So both the curl and the divergence produce different things from a vector field. There's just a quick example. Let's look at a theorem that talks about the it talks about what happens with the interaction of divergence and curl. So if you have a vector field of this form, if p, q, and r have continuous second-order partial derivatives, again, the purpose of this is because we're going to use Clairaut's theorem again, then the divergence of the curl of the vector field is 0. That's the scalar 0. Now, I do want to point something out. There's some exercises in this section which give you a bunch of operations combining divergence and curl and say, are these operations well-defined, or do they exist, or do they mean anything? It's similar to what we did back in Chapter 12, where we introduced dot products and cross products with vectors. You have to remember that the cross product of two vectors is a vector. The dot product of two vectors is a scalar. And those things need to interact according to the normal rules of, scalar multiplication, vector addition, yada, yada, yada. So this is defined because you can think of this as having parentheses here. If you have a vector field, the curl of a vector field is another vector field. The divergence of a vector field is defined, and we gave that above. The result will be a scalar, and in this case, it's saying the scalar will be 0. Notice if I were to reverse the order, if I wanted to take the curl of the divergence of f, that would not be defined. Because again, if the divergence were in here, the divergence of a vector field would be a scalar field, and you can't take the curl of a scalar field. You can only take the curl of a vector field. So this has to go this direction. Okay, but let's go ahead and prove this theorem. This is an easy one to prove, so we just calculate this directly. If you have a vector field of this form, then you're taking the del cross f, which is the definition of the curl, first. And then once you have done that, that's going to give you a vector field with these guys in parentheses as your component functions. We dot that with the del operator, so we differentiate the first one with respect to x, second with respect to y, third with respect to z. That's going to produce a bunch of second-order derivatives. Now, these second-order derivatives are going to pair up in a way that causes everything to cancel out. So first of all, notice I have a second derivative of r with respect to y, then with respect to x, and then over here, minus the same second derivative, but with the order of differentiation reversed. We know that these two terms will be equal because of Clairaut's theorem. You can reverse the order of differentiation because of the assumption that we have continuous second-order partial derivatives. So that makes the whole thing go to 0, which is what we wanted to prove. Okay? To show kind of a quick application of this, I want to show that this vector field, I should say f equals, let me change that, show that f equals xi plus yj plus zk cannot be written as the curl of a vector field. Okay, so what we do is we say, suppose that it could. Suppose g equals, let me change that. I want this to be the curl of something else. So suppose, I guess I could say that G is a vector field such that the curl of G, let's go like this, is equal to F. So that's what it's saying is we want to show that this is impossible. then if this is the case, if I could find a vector field G whose curl was the function of the vector field that we were given, and if I wanted to use this theorem, what I could try and do is take a divergence of both sides. Then the divergence of the curl of G would be equal to the divergence of F, which we can do directly. The divergence would be the partial derivative of this with respect to x, then with respect to y, then with respect to z. Each of those is going to have a partial derivative of 1, giving me 3. That contradicts this theorem because this function has very clearly, continuous second-order partial derivatives. They would all the second derivatives would be 0. The divergence of the curl of G should have come out to 0 if, because of this theorem. We didn't get that. This is a contradiction. Okay, so that shows that this could not be written as the curl of any other vector field. It violates this theorem. Okay, so keeping with this operator that we're calling del, this differential operator, we've seen it used in a couple of ways. So if you think of it as being multiplied by a scalar field f, del f, that represents the gradient of a function f or a scalar field f. We call that the gradient field. The dot product, which we just talked about, of del with a vector field gives us the divergence of that vector field. The cross product of del with a vector field gives us the curl of that vector field. There's a really useful operator that appears in numerous areas in math and differential equations and the sciences as well. It's called the Laplacian or the Laplace operator. And we notate it this way. It looks like del squared, but we think of it as del dot del. So what would that mean? Well, here's an example right here. Del squared of a scalar field f. You apply it to a scalar field in the same way that you apply del to a scalar field for a gradient. Del squared of f is the same thing as del dot del of f, and we think of this as being in parentheses right here. Okay, the del f is the gradient of f, and so del dot del f is the divergence of the gradient of f. That's what the Laplacian does. It takes the divergence of the gradient of a function f. But you could also write it this way, because we know that the gradient of a function f would be the vector field whose component functions are the partial derivative of f with respect to x, then with respect to y, then with respect to z. And if we dot that with the del operator, it's going to take a derivative of each of those partial derivatives with respect to the same variable again. So it turns each of them into second derivatives, not unmixed second derivatives. So both with respect to x here, both with respect to y, and so on. And then because it's divergence, and we think of that like a dot product, we sum those. Okay, so the Laplace operator, the Laplacian, gives us this expression right here. One place where it shows up, which I'm mentioning right here, is in what we call the Laplace equation, which is a really, really important partial differential equation. The Laplacian, or the Laplace equation, is the one that says that the Laplacian of f is equal to 0, which we could represent this way. The sum of the unmixed partial derivatives of a scalar field equals 0. This is an example where f is a 3-variable function, but the Laplace equation applies to functions of any number of variables. In fact, we're going to look at one here where we're talking about the Laplace equation of a 2-variable scalar field instead of a 3-variable, but this is just the kind of a one case that I could talk about. This isn't a huge topic for this class, but it is for other classes. Any solution to this partial differential equation, and there's lots of them, any solution is called a harmonic function. Harmonic functions are really important in a number of different areas of mathematics. If you major in math, you take a course in complex analysis. You'll talk about analytic functions, and you'll learn that the real and imaginary parts of analytic functions are harmonic. There's a number of other applications of this, but what I want to do is just verify that a particular scalar field that I'm given is a harmonic function. So how do we do that? Well, in our case, we want to show that it's a solution to the Laplace equation, but the Laplace equation in R2, which means I don't have this last term right here. I want the unmixed second partial derivatives of f with respect to x and y. So let's start with the first one. If I take the the partial derivative of f with respect to x only shows up in this term right here. That's going to give me ke to the kx sine of ky. Okay? That's going to mean that the second partial derivative with respect to x, I differentiate with respect to x, is just going to spit out another k right there, k squared e to the kx sine of ky. Now what about differentiating with respect to y? Okay, well here I'm going to get the sine of ky is the only part of this function that has a y in it. So differentiating this is going to spit out a k and change the sine into a cosine. I get k e to the kx cosine of ky, which means my second partial derivative is going to be differentiate again. The cosine is going to become a negative sine, and it's going to spit out another k. Let me bring the negative and the k out. It gives me negative k squared e to the kx sine of ky. Now, if you notice, if I add these two things, I get 0. That shows that the sum of the unmixed second partial derivatives is 0, making this a solution to the Laplace equation, meaning this is a harmonic function. That sign could have been replaced with a cosine, and we would have had yet another harmonic function. Okay, so we're not going to deal with those that much, like I said, but that is an important topic for other courses. I just want to bring that up here. All right. To wrap things up, what I want to talk about is I want to revisit Green's theorem, which we talked about in the last section. Really important theorem. What we've done in this section is given us some tools to think of Green's theorem using some alternate notation. It's what we call a vector form of Green's theorem. So the first thing I want to point out is if you have a vector field f equals pi plus qj, then the meaning, sorry, let's get a little bit more in here. Let's suppose you also have a plane region D with a boundary curve C, and then let's suppose also that P, Q, these two component functions, and the curve C all satisfy the conditions of Green's theorem. It's positively oriented curve and yada, 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 all that stuff. Then the line integral around C, or along C, of p dx plus q dy, as we've already said back in 16.2, is the same thing as the line integral of f dot dr. So this notation is an alternative notation for this, okay? But we're thinking of this more as a vector field here instead of, line integral of a couple of scalar functions. All right. Also, if I were to take the curl of f, initially it looks like I can't do that because we can only take the curl of vector fields in R3, since we need to be able to take a cross product that only works with vectors in R3. However, it's very common to do this if you want to use the machinery of a vector field in R3, namely if you want to use something like curl on a vector field that lives in R2, you can do what's called an embedding. We're going to embed this in R3 by giving it a third component and just making it 0. So I could think of this as exactly the same thing as f equals pi plus qj plus 0k, and it doesn't do anything differently as far as how this vector field behaves. So by doing that, the curl of that vector field would look like this. If you were to go and compute the determinant here, you're going to notice that the only non-zero term is the k component of this curl. So we end up with the partial of q with respect to x minus the partial of p with respect to y. Compare that to Green's theorem, though. In Green's theorem, where we evaluate this line integral around this closed curve C, the double integral that Green's theorem says it's equal to has exactly this. at least the part in parentheses, as its integrand. Okay, so this is giving us something that looks very, very similar to the integrand in the double integral of Green's theorem. But the k is kind of a problem, because in Green's theorem, that double integral should be of a scalar field. We don't do double integrals of vector fields. Right now, this is a vector field because it has components. I can do away with this component by dotting it with k. We know that k dotted with itself is equal to 1. We showed that way back in chapter 12. So if I dot the curl of f with k, it's going to turn that k here into a 1, which basically means it kind of goes away in a sense, and I'm left with the partial of q with respect to x minus the partial of p with respect to y. That's the integrand that I need for Green's theorem. So according to Green's theorem, this line integral, which equals this, which equals the double integral over d, the plane region that C surrounds, of this, which would be equal to the double integral over d of this, since this is equal to this. So this is what we call a vector form of Green's theorem. In particular, it's one vector form of Green's theorem. If you remember the way that we defined line integrals back in section 16.2, where we talked about line integrals of vector fields, our derivation of that used a unit tangent vector along that curve C, and we said that this line integral can be called the line integral of the tangential component of f along C. So I'm actually kind of running out of time in this video. What I want to do is, in the next video, show that there's an alternative way of thinking about this, where the line integral is not of the tangential component, but of the normal component of f. So we'll go ahead and do that in the next video.